title a little bit, and you can see what I was trying to do is to give a brief summary of where we are today in astronomy on circumstellar disks and planets. So the connection to astrobiology is more on the astro side than on the biology side, of course. And as Axel remarked yesterday, this is very much mainstream stuff and perhaps not so interesting for the biologists. But the experts in the audience on disks might get a little bit bored. I take the risk and am a little bit explicit in the beginning. Now, as you are aware of, the idea of a solar nebula, that is of a disk which was forming the solar system, has retained its actuality even until today, and disks are in the fashion, and our understanding of these objects is not very far from the original ideas from the 18th century. There is another component which has been added about 25 years ago, and these are these plasma jets which are streaming out at very high velocity from young stellar objects, which are during the formation creating these rotating circumstellar disks. And jumping onto the bandwagon, as everybody else in this field, we ignore the jets when we talk about the disks, which is perhaps not the most clever thing to do, but for the moment I will stick to the conventional way of looking at it. And the main features of what people have identified today are shown in a schematic way here in this little video, where we see how a planet, which you are perhaps can imagine is orbiting the star. There's only one planet in these models, as normal as we have seen yesterday also, although planetary systems can contain more than that. But the interaction due to the planet, it will clean an inner gap, perhaps, and this is not the gap I heard before. You were talking, Axel was mentioning a region of the size of about an astronomical unit or something, which is due to interaction with the magnetic field, I assume. You were referring to the dead zone. Right? Here it is this is a purely gravitational collisional interaction, which is clearing the disk from at least the dust particles in this region. You can perhaps also imagine that there is a tilt in the disk, warps, there might be excited spiral waves and what have you. And these concepts are, of course, based on numerous observations of quite a number of disks today, both resolved spatially, and most of them are not resolved spatially, but one infers the presence of both gas and dust, depending on the time scale. I come back to them, that essentially all of these objects have central holes in most cases, and one can even see in spatially resolved things, warps, clumps, spiral waves, and an interesting, from the dynamical point of view, perhaps, is the existence of very sharp outer edges. The whole thing then becomes some sort of an astronomical zoo. And on the other hand, we have lots of planets discovered, as we heard yesterday. A couple of days ago, the total number officially announced is more than 260. And they have all kinds of sizes, not the ones we want to see when it comes to life expectation on planetary surfaces. Most of these planets, as you can see, they're on the order of Jupiter masses or larger. And they are found around both single stars and binaries and what have you, and they are on tight orbits very close to the star. This was a very big surprise. That was the way they were discovered. But nowadays, as time progresses, because of the orbital timescales, more and more also on wider orbits are found. And a large number have the very strange property to be on highly eccentric orbits, and some of the objects, one has discovered one single planet, and there might also be multiple planets around it.
Could Jupiter be detected by somebody else?
Yes.
Yes. So if they observe
We are on the verge about 12 years orbit. Timescale means 25 years of monitoring, at least 2 orbits. We are coming there. I think the most distant is on the order of 3.5 AU right now, just between, that's the distance of the asteroid then. Now, you have observed lots of planets and lots of disks, and we would then perhaps expect lots of disks with planets, which makes it interesting then from the astrobiology point of view eventually. And of course, this is a matter of time scales. And very schematically, we run through from year 0 of formation of the star and its planets down to a few billion years here. As you can see, the star is believed to be formed within a few 100,000 years, maybe even less, and is accompanied by the formation of the giant planets, which stops about up to 10 million years. Why 10 million years? Because at that time it is believed, or it's observed, one can say, that the disks which have contained a lot of gas, which is forming these gas giants, essentially is dissipated and has left the system. Maybe has gone into planets, and some of it, or quite a bit of it, will have to be expelled by these outflows I was talking about. And these are observed up to a few million years. And then we lose sensitivity. An outflow of the size of the solar wind we would not be able to discover or detect at these distances. After the loss of the gas, there are still the disks around, and these are the disks actually we have seen on the pictures before. Some of these resolved disks are more of that kind, which we call the debris disk, and that is due to the fact that because of the timescales of 10 to perhaps 400 million years, the collisional timescales are much shorter than the lifetime of the disk during which these objects are observed. And that is due to the fact that big particles in the dust disk would spiral in towards the star and disappear on timescales from 10,000 years to 1 million years, depending on the details, whereas small particles would be blown out by the radiation pressure which is working on these particles. And also there, timescales are very short compared to the lifetime of the disk. Now, this is an empirical number, these 400 million years. To have the connection to the solar system, let me say, I think the moon is believed to be formed by about 50 million years, and this is the late heavy bombardment in the solar system around this time. The planets, on the other hand, for them, the age estimates of the stars, that is, with the planets, have been observed essentially over all timescales. The youngest object is perhaps 1 million years old only, whereas the one which fits on this plot here is about 5.5 billion years. And this is very strange because this star, 55 Cancri, seems to have an affinity with the number 5. It is 5.5 billion years. It's called 55 Cancri, and it has 5 planets around it. It's a strange. Now we would then expect, if we overlay the timescale, to find disks and planets over quite an extended period of time. Naively. So there should be plenty of these guys around there. So a question, how many do you expect? Pick a number. We know about, say, 260 planets, say 260 disks. So how many of these guys do you then expect to find? Now the number of known objects are 2. And that's a little bit embarrassing for several reasons, as you will see. And one has been discovered about almost 10 years ago now, which is it's a star called Epsilon Eridani, which has been famous in the literature for this reason. And the planet has been confirmed only just relatively recently. It has been it had been suspected for a long time, but the true evidence by the radial velocity technique came only quite recently. You can see there is a dispersion in the age estimate of this thing. It is estimated between 800 million years and 2 billion years, and that gives you an indication on what the uncertainties are when it comes to the timescales which are involved. Now, the other star, which has a planet, has even a larger spread in age estimates from 300 million years to 4.8 billion years. So this, of course, is reasonably, or is relatively meaningless to talk about the age of the star here. It gives you a good feeling for how bad astronomy can be, but it can be good as well, right? And there might be another one which is not really of the kind of these things, because these are evolved stars. There might be recently a detected one, very young objects. Now, actually, as we know, there are three, right? There is also, we should not forget about the sun, because we have so small number statistics here so that everyone. Are these objects freaks, including the solar system? Because if they are freaks, then we can close the session today. Well, why talk about astrobiology? Biology is fine, astronomy is fine, but combining the two would be rather not very compelling. If one puts the evidence, at least a few years ago, onto a graph which shows the time scale versus a measure of the amount of dust, and here these, as you can see, are logarithmic time scales. These are 8 orders of magnitudes. Here we go from 30 million years to 10 billion years. There you might get the idea there is some sort of relationship in this log-log plot. And one has speculated that if one fits this data with a straight line in this log-log plot, then one can also have some theoretical ideas about that this line could reflect collisional processes and be associated with a time scale of collisions between particles and bigger bodies. Now, the debris dust, the stuff you see, is very small. These are small dust particles which are believed to have been produced by collisions of much bigger particles, but these things we don't see. But we would like to. And particularly much more updated version of a similar plot has been presented a couple of years ago. And here, these people show observations in the sub-millimeter millimeter regime, and there these received energies are directly proportional to the mass you're observing. And of course you see a very large spread of essentially upper limits. These people haven't discovered any or detected anything except a few cases. 3 in 1 year. This guy I showed before, this very young star is up here. This Epsilon Eridani is down here. And the stars, these planets they have been observing, they are all down here and have not been discovered. This is the line we saw before. Of course, this line doesn't make any sense. The other star with this enormous uncertainty in age is sitting up here, which we have recently discovered that it has a dust disk around it. We knew it had a planet, but we now also know that it has a dust disk around it. So a question then, perhaps we can skip this, how this is determined, but the bottom line is that one has to know the temperature and the opacity of the material in order to we can skip these technical details. The bottom line is that we need to know the temperature of the grains at any one distance, which of course is a distribution in a disk, and this is dependent on the grain size as well. Smaller grains are less efficient in radiating off as bigger ones, and so that one gets a dispersion if one has an ensemble of different sizes. Coming to the star, which I just pointed out in a previous graph, this one which is called Q1 Eridani, we see, and this is fairly well determined, this curve, which is not dependent so much on the age of the object, it depends on the characteristics. So what we normally see in the optical is this upper part, then you have several order of magnitudes on either the ultraviolet side here from 1,000 angstroms down in the far infrared. The thing is down by at least 2 orders of magnitudes or so. This is a stellar atmosphere model for the star, which is fairly close. It's almost like the sun, not very different from the sun. If you put in the data points which have been obtained, here there are much more. I just show this for the normalization. But these interesting points are over here in the infrared region, longwards of 10 microns. You see here, the infrared emission by the thing seems to follow the star quite nicely and is simply defined by the stellar photosphere. But then there are some things sticking up here which are significantly above the value of the stellar photosphere, and here we get the idea there is an extra component. Then at longer wavelengths, with satellites, one has discovered these points here and measured them, and this gives you the idea here, these are definitely clear detections. These are several orders of magnitudes of the stellar band. Then there has been an observation over here at 1.3 millimeter, which has not detected the star, and then there is our little point here. Now, all my story today is about this little point. One point, and it makes a difference. Because if you produce a fit of the spectral energy distribution, then you will see that the excess is fit by a black body curve of one value, one single black body. And this is very bizarre. Earlier data were much more inconclusive. They have not even attempted in this point here, these guys which discover or which deduce the upper limit here. There is a fit. I think we can see the data points here. This is not even a fit, I would call it. So the implication or a straightforward interpretation of this is that if you have a single temperature black body, this means two things. First of all, the particles are very big. They are much larger than the wavelength of observation. And this would be, if you have only one temperature, will be consistent that you have a narrow ring around the star, where you have not a big or a large temperature distribution around it. And in this particular case, the ring would be at the orbital distance, which corresponds to that of Uranus, and as you know, the planet is about the size of Jupiter and would be in the solar system situated at the inner edge of the asteroid belt. Now there is other information which supports the view that the particles are big. They are much bigger than the interstellar particles, and that is in the 10 micron regions, here 8 to 12 microns. One has obtained spectra, and here from 10 to 30 microns, and these are essentially flat. There are no features. If you would have particles which are comparable to the wavelengths and in this disk, then you would see features of this kind, silicate features or spectral signatures of the material. Now, in order to interpret this quantitatively, we have a good understanding of the temperature, as I said, but the idea about the value of the opacity is quite difficult to assess here. And in particular, if you have a black body curve, there is no information on the particle size. This is, we talked about information yesterday. Black body radiation means essentially thermal equilibrium, and equilibrium means zero information, essentially, except the temperature. So here are then calculated and partially measured curves of the opacity, that is the mass absorption coefficient of various materials and grain sizes, which are indicated here. from 0.3 micron to 3 millimeter, and then there's something called beta peak, which is a disk around a star, which is very different from what we have. Now, what we do not really know is what is the, and here again, this is logarithmic scales where we should put ourselves. But if we make a reasonable assumption of that, or just coming back, if we use opacities which are generally used, 3 different curves here, you can directly see these do not fit the data. There is no way using known opacity curves in order to fit the data. On the other hand, the concept of grain growth would be consistent with the data, and maybe here is the only present connection with biology in some sense, perhaps, because on these grains which are growing in size quite dramatically, as we will see, there could be ice coatings, which gives rise to the concentration of volatiles, and they could act as catalysts for molecular growth and maybe go to, this is very speculative. I just put it in this morning because of your comment yesterday night. Now what we see in the interstellar medium is that the well-known opacity curves of interstellar material is based on this part, essentially. To some extent also this one. And there you can see that grains in the interstellar medium are generally very small. The standard form cuts off here by 1/4 of a micron. There are indications from previous results that there might be grains of the size of millimeters, as we have seen before in the curve. What one has measured in theater in the interplanetary space are these kinds of grains, which are at least 10 microns or larger. And the size here is biased by the measurement method, and I don't think one has a good idea of how big grains can be in the interplanetary medium. And planetary disks, however, we need to go through from the submicron regime to grow the grains to centimeters and to decimeters and to the meter. And theorists, they claim that this gets increasingly difficult to do, but they say that, oh, we can perhaps make this one. In order to give rise to debris disks, however, and planets, we need to come into this regime. Planetesimals are on the order of rough numbers 1,000 kilometers across, and they are stirring the disk, and they are colliding and giving rise to this debris stuff. Right? And we need them in order to become gravitationally unstable enough to accrete in a runaway process the gas which is in the early disk in order to create the giant planets, which have to be formed before 10 million years. Whereas the rocky planets, the time limitation is not that severe. So the critical size is really this one, and if we concentrate or focus on that for a little while, and just to repeat this, that if we know the temperature and the opacity, then we know also the mass of the disk. This is straightforward. And this should then also perhaps be consistent with the number of parent bodies, which gives rise to these smaller particles. Now, in this particular case, the mass of the disk is comparable to the mass in the Kuiper belt of the solar system. And in order to estimate the number of radiating particles, we have to assume something about the particle size distribution. And if we use a standard case, which is obtained for collisional processes, then we see that if we just pick a number, 50 microns, which is close to the energy peak of the distribution, then we see that we have almost 100 million of this kilometer size and something like 20,000 of the 10 kilometer size things around there. And that's about how far I have come to that. To give you an idea, what we talk about is this IDA and its moon ductile, and this thing is about 1 kilometer in size, and this is a gravitational bound system in our own astrobio. So in order to go ahead, and I haven't been there yet, these observations were done in August this year, And what we need to have a better understanding of what the timescales are for the collision processes here, and this needs very detailed modeling, numerical modeling. And we have to understand whether this is compatible with a steady state, or whether we have to advocate to a catastrophic event, something like the heavy bombardment we had in our own solar system. And if you need, or if you are forced to pick this choice here from these models, then we would like to know what is the frequency of these catastrophes. And of course, as always, we need better resolutions. So this would be my conclusion, since which I said it before. But before this, I want to make some announcement here. As Leonard pointed out yesterday, I think we should not give up to support the Darwin mission, which brings us back to the astrobiology aspect of this. Thank you very much.
So, questions for René?
I had just a comment. You described these various steps in sizes. One of the most traditional big problems in formation is the 1 meter size object, actually, at which point they become very strongly migrating and having big trouble actually staying in the disk. This might be solved, being in process being solved now using turbulence and so on. So yes, that's a note.
No, I'm just referring to what one of the experts in the field, Thomas Henning, said a couple of months ago. So there they claim that they can make the meter size now.
Yeah, yes.
Theoretically.
But that's still.
But that's the end of the story. Then they have a huge problem of getting into bigger particles. But here we have an observation. I said this point is really significant because it gives us an idea how many of these big particles could be around them, with the associated uncertainties, of course.
But that assumes a debris scenario, well, if you look at the solar system, it's not quite clear, but the zodiacal dust seems to be a mixture. It is obviously a mixture of cometary, sort of expelled material and collisional debris, and we know from some cases, in particular beta thick, that there are cometary similarities, similar bodies like comets, but much more frequent and much bigger than we have in the present solar system. So what I'm thinking is that this could be maybe a similar case, or maybe even the reservoir of comets that you are seeing.
I think this thought in a way gives us a clear message. This thing is quite displaced from the rest here. In that case, and also in that case where we have spatial information, we know it is not the zodiacal dust we see. It's something like the Kuiper belt. The distance of the stuff here by the fit is about 20 AU from the star. It's not 1 AU. But of course,
out of these 260 planets, how many of them are orbiting a star which is very similar to our Sun?
Most of them, because by the way they have been selected. There is, I did not take this up, but there is a selection effect in here. These stars are, maybe you know at least Vega, right? These guys here, which are identified, they are more massive than the Sun. They are hotter than the Sun, and that's where one has initially also discovered the biggest the disks around them. But these stars are not suitable for the detection technique one is using to see the planets. They need a lot of spectral lines in the absorption spectra, and these guys are essentially featureless. There are only hydrogen lines to first order in the spectra, and they're very broad, which makes it difficult to attain sufficient precision. So there is a high bias in it. Whereas the interesting thing with that one is that's actually what you call it's a star which is a little bit less massive than the Sun, but it's similar to the Sun.
I'm sorry, you probably said it, but I missed it. The circles you have around, what do they mean in this?
Oh, that's just to
okay, yes.
give the intention.
I see. Okay.
These are the three stars where we know they have debris just around them with planets. That's it.
Axel?
So, if I understand correctly, there's no conclusive evidence really for the grain growth scenario, although it may be there. You think maybe there are stages with millimeter-sized particles preferentially.
It comes as indirectly fitting the spectral energy distributions.
So maybe this line of evidence can be improved this time, of course. But the other opposing scenario would be the disk instability scenario. Can one possibly, based on observations, exclude that scenario, that competing scenario?
You mean Alan Boss?
Yeah. I mean, you would then perhaps expect more large-scale inhomogeneities.
I don't think anyone is excluding either of the scenarios. There is, however, Alan Boss' theory, and that is the idea that you have a gravitationally unstable disk, and that you have locally, like in the case of star formation, dynamical collapse. The nice thing about this model is that it has not the problem with the timescale of giant planet formation, because this thing proceeds very quickly. It has, however, the problem of producing planets like the Earth, Mars, Venus, and so forth, the rocky stuff. It produces only major mass planets.
Yeah, right.
Yeah, I'm having a very naive question. Why is it a problem to get these bigger objects formed? Yeah, you can see them around. So they were formed. So it happened, obviously.
Yes. There is a problem of the internal strength of the material to keep it together.
I mean, if you imagine two balls bumping into each other, what happens? Will they form this bigger one, or will they split and you have four smaller ones even? That's the problem.
So it's material dependent and size dependent.
Time.
Sorry?
And time.
Time, yeah. Yeah, I don't know, time in a collision.
Well, no, but in the bigger sort of disk survival disk time sense is also a problem.
But do they have to form this way, that smaller balls from bigger balls, they cannot form at once?
That was exactly the
That was
scenario.
yeah.
Which is this.
And I said that it appears to work for the big planets like Jupiter and Saturn and so forth. They have already problems with doing something like Uranus or something.
But that's just based on model calculations, and maybe those
everything
are
is
not
based on model calculations. Everything is based on model.
Yeah, right. So therefore, it's also not conclusive, really.
Yes.
Because it's all resolution dependent. So maybe it's too early to give up on other ideas, especially if none of these scenarios are completely certain yet. No, you don't.
Yeah, no. That's why we are going on and try to pursue to have an idea.
Yes.
What we see.
Yes.
One important point perhaps is how many of these planets, 260 planets, are around young stars?
As I said, there were a couple or so, very few.
So maybe it's not too surprising that since the disks go away, the planets haven't been observed too often in combination with disks.
But the time scale is only 10 million years of the gas disks.
But if they're only like a couple of planets, moon, which are younger than 10 million years. Then you wouldn't expect more than a couple of planets to be in the system of this.
But we have lots of disks at all time scales.
Yeah, but as you said, it's a biased sample for stars that we have not the tool to find planets around, so it may be the explanation. But maybe we should add that there is, for the Herschel mission, there are at least proposed programs to find disks around the solar, to find disks around solar-type stars and in our neighborhood that has not yet been detected because of sensitivity reasons. So this picture may change.
Okay, maybe we should stop here and thank René. Our last speaker has arrived, but before that is Raphael Chasson, who will talk of theory of proton metabolism. Raphael is a guest researcher here at Nordita.
Okay, so I will speak back about emergence of proto-metabolism. So what are these proto-metabolism? It's some kind of terminology that we just start to see in the literature. So actually it's very simple. The question is just to wonder how a chemical system, whatever it is, can manage to use energy, whatever the energy is, to do stuff, whatever the stuff is. So okay, this is very raw definition, but what I will try to explain you is, okay, just try to understand what is behind this notion of chemical systems that can use energy, and try to manage to find a much better definition that I've just given to you. So, for doing that, we just start to study some very specific chemical systems that are able to present bifurcation toward the homochirality. And these are very quite simple chemical systems, but we will be able to see how chemical networks can work. So the homochirality is this very fundamental property for the molecular origin of life. And so the problem is that chemical system, initially if there is no life, just have to be totally racemic. That is, you have the same quantity of right and left configurations of molecules. And there was these Frank models developed in the early 50s that was just explaining how you can observe a bifurcation from a racemic state to an all right or all left systems. And it's really based on this very simple network. That is, we have some matter flow from reactants into products. And these systems can generate the formation of molecules that can be either L or D, right or left. And we have the fact that we have some autocatalysis. That is, the L has their own formation and the D has their own formations. And these dynamic systems allow the unstabilization of the racemic state and the stabilization of the all L or all D states. That is, we have this bifurcation system that is, even if you start from a racemic state, this state just can't exist on its own, and you will stochastically evolve towards an all L or all the states. So what's interesting in this approach is that we have to study the chemical network rather than the single reactions. Because if you have just an autocatalytic reaction on its own, you can't say, okay, it will bifurcate, it will do stuff. No, because what is really important is that you need collective behaviors. You really need several reactions working together so that you can observe some global network autocatalysis. It's really the behavior of the whole network that is important. And what we can do in this kind of system is that homochirality can really be obtained just as an emergent property. You have these systems with lots of reactions working together. And in this system, you can observe some properties that are emergent. So how is this working? And how, just starting from chemical networks, we can see something that can be called protometabolism. So, just start again, this is again the Frank model, but now it's much more the thermodynamic point of view. So what happens in this model? We have some reactants that are transformed into products. We have this spontaneous reaction that is possible. That is, we have some difference of chemical potentials. And so we have these continuous transformations that goes through these L and D compounds. And as long as we have these transformations, it means that there we have the autocatalysis that can work. And then if we have continuously this autocatalysis that works, we can observe the bifurcations.
With chemical potential, you mean potential energy? Is that what you mean?
It's the thermodynamic potential, actually. The affinity of molecules linked to the delta RG and the...
U is...
It means that. Typically, this potential means that if you have the flows, you will maintain a high concentration of air and a low concentration of P. So that is, air will have a high concentrations and P a low concentration. But if you cut the flow, there is a diminution of the concentration of air and the concentration of P, and so the change of this chemical potential. It's not, it's really the macroscopic value of the...
It's not the potential energy, so it's...
No, it's not potential energy, it's not linked to energy levels. It's really the thermodynamic property of the systems related to it. So it's really proportional. It's proportional to the activity of, that is really proportional to the concentrations of the species, and but it's also linked to the energy of, to the potential energy, in the fact that very unstable molecules will tend to have high potential, and very stable molecules will tend to have stable lower.
It's defined as density of the reaction per mole. That's the mean.
Yeah. Okay. So okay. And so, okay, and what is important is to maintain this difference of energy. So that's why we will need this flow to maintain this difference, because if we cut the flows, we are equilibrating, we do not have these spontaneous transformations. That is, the autocatalytic system does not work anymore, and the system just go back to what we said. That is, when all the chemical potential become equals, we are at the thermodynamic equilibrium, so nothing happens. One other way to perform that is to perform actually the recycling. Especially if we are working in this prebiotic chemistry, all the organic compounds may have been quite scarce, and having this open flow is not very good, because it would require that we just continuously build amino acids, for example, and destroy them. Not very good. So another way that is much more interesting is recycling of the products back to the reactants. And what we have actually is that we can find a way to transform the products that are low chemical energy, low chemical potential, back into higher potential molecules. And if we maintain this by some mechanism, we can continuously maintain this reaction of air to XL and XD or E and back to air. This will work also. We also see some bifurcations because we continuously have these catalytic reactions. And what's interesting is, it means that we are generating cycles of reactions. And cycles of reactions are very interesting because up to now I was just saying that, okay, we have autocatalytic reactions. Autocatalytic reactions are great because they can do very interesting stuff, they are highly nonlinear, but how can we build them? And once we have understood that we can quite easily generate cycles of reactions, it's interesting because once you have the cycles, you may generate some global autocatalysis inside the network, even if you do not have autocatalytic reaction. So let's see how this can work. So just imagine that we have a cycle of reactions. So that means we have compounds that is stable. We activate it. We just input energy in the system so that we can form A. A is of high chemical potential, so we can spontaneously react into B and back to C. And so we have the cycles. If we just have that, it's not really important. What it means that we input energy there, and there we are just the dissipation of entropy, and okay, we are just consuming energy for doing nothing. But if we could have something like that, it could be very interesting. So if we have some XL compounds, we input energy, we form B, and B can form 2XL. It means that after one loop, we start from 1XL and then we have 2XL. So we can see that if we can manage to have that, we can have some auto amplifications. We can have exponential growth of this compound. Okay, if we just have that, this doesn't really look like chemistry because there is no mass conservation. So okay, just input another compound. And this is a network autocatalysis. That is, globally, we have R plus XL that react to make A, D, and then form to XL. So globally, we have the compound, the reactant, that is transformed into XL, and that this process is actually activated by another XL. We have a network autocatalysis that is really composed of several single and simple reactions, no direct autocatalysis, but you can generate autocatalysis inside networks.
But you said exponential growth. I mean, would that require also that you have almost unlimited amount?
Yeah, of course. I mean, it tends to be exponential growth. Of course, it's not the only process. You have some fixed quantity of matter, of course. Yes, yes. And that is actually, this will work as long as you maintain the air. And so, and this is activated, behavior. We have to input energy so that we input energy, and the energy just forces the transformation of into XL. Okay, of course, its energy can be input indirectly. That is, we can add some kind of energetic compounds and some waste compounds that will force this reaction. That is, we can have some coupling of one reaction that we can transfer the free energy of this reaction from this flow to this cycle. So globally, what we can see is, if we study all these simple systems, all seems to work like, okay, you have this kind of linear flows, and you have these cycles, and you have the association between these linear flows and these cycles. So what happens actually in a very general network? So for that, we just can apply the metabolism formalism, that is a mathematical formalism that is used by the biologists to study the metabolic network. These are very complex chemical networks and can be used to understand what happens. So let's apply that to very complex systems. So if we take back these catalytic cycles, the idea is just we can have a matrix that represents this system. So I won't enter the details here. It just means that you have the first reaction, second, third, etc. And this you have A compound, B compound, C compound, D compound. So you see that the first reaction is A plus B that gives C. The second reaction is C that gives D, etc., etc. And what's interesting is once you have this matrix, you can do maths. And with this mathematics, you can understand lots of stuff of this network. So if we start with these global networks, typically what we first thing that we can take is that we will be able to decompose it into cycles. That is, won't give you the details of the mathematics, but you can perform the decomposition. That is, you can say, okay, that's actually what is behind this systems, we can decompose it like that. So what does it mean? If we switch back, we have A and B, that's right, to make a C. So if we just look at the mass balance of these reactions, it means that inside the C, you have something that comes from A and something that comes from B. So you can take that, okay, these are two fundamental elements that we are just glued together. And if you look, if you perform this kind of decomposition of molecules with the sum of all the reactions, you can totally decompose the system. And that is, we have only one symptom that is called ACE. And so this symptom ACE is in A, and this symptom is in B. When it reacts, we have two symptoms that are in C. When it becomes a D, you just form two symptoms that are in D. And when it breaks that, you break down and you form two symptoms that are in B. And so, if you perform now another step of decomposition, that is, you first decompose molecules into symptoms. Now you can decompose the systems into this. That is, this autocatalytic network, actually we can just see like that. That we have ACE A, that becomes AC, that becomes SD, that becomes SD. And you have the cycle of SD, SC, SD, etc., etc. So that means that this very simple system, we have a cycle that is coupled to a linear flow. And what I've shown you on these very simple networks, actually, it can be performed on any chemical systems. So the importance, what the meaning of that is that whatever the chemical systems is, you can always decompose it as linear flows and cycles, and everything is coupled. So the image that we can have of chemical systems is this kind of mechanism. You input energy, you plug energy into these systems. This energy will generate flows. And to these flows, you will be able to connect cycles, and these cycles will just be forced to run again and again as long as you have the energy. And all these networks are composed of all these flows and these cycles. And this is actually very interesting. So what happens if you have just a little more complex network, and we have several cycles that can communicate between them? It's very interesting because we can see that we have some cycle competitions. So typically, if we form this system that is just slightly more complex, that is, you have one autocatalytic loops there, and another autocatalytic loops there, and they're just communicating. So what means in this? We have some autocatalytic systems that will tend to transform a molecule into S, and so the S take A to make another S. So we have this positive feedback of this cycle that just make more of its own components. And by symmetry, it's the same for air. You have an air cycle that consumes A to make other of its own components. So you have also a positive feedback for this. But between them, because they are just consuming the same compound there, you have actually a competition between them. You have a negative feedback of air to S and S to air. And so if you look at this system, you also perform a bifurcation system. If you input enough energy so that the two cycles are acting very actively, you will perform a bifurcation. That is, you may observe a disparition of air and the growth of S, or the opposite, the disparition of S and the apparition of air. So,
could you just point to, you have two type of things happening here.
yeah.
Stereospecific polymerization, can you point to this?
It's very specific. It means that the air, when you don't form some air-S polymers actually. It's the air, when you have an air2 reactant A, it only forms other air. You don't have an air that reacts on A to perform some S. So it's just a perfect orientation. The air only makes air, and the S only makes S.
And where is the crushing, mechanical crushing, where is that taking place?
Okay, actually this, it's how we can perform this experimentally actually. Just for the moment I just presented to you like something very theoretical, but this is an experimental system. And this system is based on crystallizations of sodium chlorate. If you take sodium chlorate are these active water compounds when they are in solution. And when they crystallize, they can crystallize in two forms that are right or left. So if you, and this is highly selective, you form only air crystals or S crystals, not mixed crystals. So you can perform that. And if you perform this crystallization with a crushing of recycles, that is practically you have you input some ball glasses inside the system, and you have a high steering of the systems. And this, all the glass balls allow to crush the crystals so that you break the crystals that you have formed, and so that you generate much more smaller one. That is this energy of input is that we have large crystals, we have a mechanical energy that breaks down, and we just as that. And this crushing just inputs this this dynamic. And so that in this kind of system, these are experiments that were performed by Widma maybe 2 years ago or something like that. And this experiment is really that you start with a mixture with 50% of air crystals, 50% of S crystals, and you just perform this activated crushing, this strong steering, and after a moment, you have only air crystals or only S crystals. So it's really showing how chemically you can perform this kind of competitions.
So that's just another example. It's not really, that's of course not chemistry anymore then.
It's chemistry or physical chemistry,
It's
of
the
course.
same mathematics.
Yeah, it's, I don't know if there is such strong difference between what is chemical and what is physical actually. Okay. The energy is not chemical, it's physical energy. Yeah. But, okay, but the idea is there. And, okay. And okay, so what is really important in systems, okay, we have to maintain a non-equilibrium state. We input energy, and because you have all these feedbacks that are generated inside this network, you can have these competitions and these bifurcations. So this leads us to what we can call the proto-metabolism. So when we are looking at chemical network, what we can see is that we can transfer energy inside the system. And when we input energy, this energy can generate internal cycles of reaction, because we have low potential compounds. We input energy, they get higher in energy, and if they're higher, they can perform lots of reaction and go back to their state. So energy, we perform these cycles. And what is interesting is that at the moment that inside this system you perform all these cycles, you maintain this cycle, you can observe some kind of competitions between these cycles, and this competition can lead to bifurcations. And if we have some bifurcations, it means that we have some compounds that can increase, and so others that can diminish. But then you have some kind of evolution of these systems that is quite stochastic, but that leads to global structurations of the reaction network. You have some change of topology. So at first you start from chemical systems that may be totally random. You may have lots of simple compounds that react with each other with no selectivity. But once you have this kind of bifurcations, of competitions, you can observe the self-structuration of this chemical network. You can have this change of topology. And so, in this case, we may talk about protometabolism. And how we could define this protometabolism is that these are the spontaneously organized reaction network. And what makes the organization of these networks is just the influence of the energy flow inside these systems, and that these energy flows generate all these feedback loops and all this dynamic of the systems, and that lead globally to a chemical evolution. And this is really the idea. Of course, at this moment, we do not have any something that looks like Darwinism evolution. It's really chemical evolution, that is, we just have a chemical system that may evolve in one direction, in another reaction, and you can have some kind of structurations at the level of the networks. But the idea is that in this view, we can have some kind of self-organization that may be very important at this level. So, okay, so I think that I may stop here. So, okay, so thank you.
Okay, questions for Raphael? There will also, of course, be a discussion session afterwards, but I think a lot of things pop up right now.
Other general ways of predicting useful possible networks. I mean, obviously, if one doesn't really know which chemistry one is going to have on the early Earth, for example, one cannot really make much progress. One really needs to know the details of the chemistry. There's no
but
general prescription possible, I suppose.
Yeah, but actually I think that when, especially with this view, I think that what you just show what is important to look. If you want to understand how life could emerge on Earth, it means that what the first thing that we have to focus is energy. Because if you have no energy, you're just a chemical system that is at equilibrium or close to equilibrium. So actually, there are one very fundamental point is where is energy available, and where and how this energy can be used. And so I think that what we have to look for is to just okay, we have to know what chemical compounds are existing in some kind of environment, what kind of energy can enter inside these systems, and then, okay, what can happen? What can perform these chemicals with this available energy? And what kinds of dynamic can be established in this kind of systems? And of course, this is, I'm speaking about chemistry on the Earth, but it may be in astrochemistry, it may be in lots of kind of systems. And the idea is, okay, we have chemistry, we input energy, what happens? Wherever. And I think that even if it's very simple systems, energy can push the system very far from the equilibrium, and we can see very interesting behavior. Even if we are very far from life, we can see some very dynamic behaviors and some kind of autocatalysis, some kind of bifurcations, some kind of chemical evolution, even if we are totally far from life. I think it's the main idea there.
You pointed out that homochirality is a prerequisite for life.
Yeah.
And then you showed how these cycles can enhance one left instead of the other.
Yeah.
But it's not clear to me what is really the mechanism that enhances one over the other. I mean, the energy must be identical.
Yes, the energy is exactly identical.
So how can you enhance one?
It's because it's self-replicating molecule.
Yes, but why is this not happening for both of them?
Yeah, because they're just consuming, because they are, typically in this model, that if one starts to increase, it will increase its own quantity, so it will increase.
I can understand that if you start with, and if you can get a small shift, but what is causing this small shift? That's what I don't understand.
The small shift is statistical fluctuations. These are chemical systems.
Some sort of spontaneously.
Yes, of course. These are chemical systems. You have a fixed number of molecules, so you always have statistical fluctuation because you can't have exactly the same number of L molecules and S molecules. So anyway, in any systems, you can have this. You always have these small fluctuations, and actually it's proportional to if you have for a system of N molecules. The average enantiometric excess is 1 divided by it's n power minus 1/2.
So you mean that the reason we are only left-handed is just a...
Yes, it it can be just a bifurcation. But of course, it's also the problem of this system is that because the statistical fluctuations are very low, it may require a long time so that they are important enough so that we reach a totally non-racemic state. So it's possible also that this kind of system may have been seeded by homocarities that have different sources. Typically, you have these experiments or these determinations of non-racemic amino acids in meteorites. And it's possible that you have all these mechanisms that allows the symmetry breaking formation, formation of non-racemic amino acid in space, and if it's possible, of course, this can continuously seed in mostly in one direction in the whole Earth. And of course, if this is possible, it will speed up much more this symmetry breaking. But the fact is that if you don't have this kind of mechanism of Earth, nothing can happen because the enantiometric excess from space just go into the ocean and in a few hundred years just racemize totally. So we really need the two. Well, this is fundamental, and the, from space can really speed up this. So I think it's roughly the idea.
So in which form do you envisage that the energy enters the cycle? I mean, if you have this happen, say, a dispersed system like aqueous solution or something, you need a strong gradient in mu to have things happen. How do you initially build your strong gradient system?
What I said. What the more fundamental point, very initial point is how we can input energy into this system. This generation of difference of chemical energy that we need to input energy. And what it is, it can be some photochemistry that generates some very active molecules typically these kind of systems, I study a lot these kind of systems based on the reactivity of amino acids. And you can understand this creation of high difference of potential can be made by activating the amino acid into the it's what we call the NCAs, that is the activated amino acids, and there are lots of ways to perform this kind of activation. So actually, yes, we need some energy source, but there are lots of possibilities to form this energy.
Right.
Can you do this homochromatic synthesis without a surface? Can it be done in solution?
Well, yes, actually, yes. It's right that if you do that by crystallization, it's the more easy because you have with this surface you have these really strong interactions, and most of the chemical systems that were performed and that were allowing this symmetry breaking were based on crystallization and with this strong surface effect. But you have very few for the moment reactions that allow symmetry breaking in solutions. It's typically the reaction of SOI. That is, there are very specific reactions, and that are based on very specific autocatalysis. And I don't know well, it's some kind of reactivity based on organozinc, some zinc compounds, and you have this really very efficient transfer of chirality. And what so I could show is that even if when you were starting from a racemic mixture, it was performing manually some several steps of reactions, and at the end he obtained a very high enantiomeric excess. So you can perform in solution this kind of symmetry breaking. But for the moment, the problem is, okay, it's on very specific chemistry. And what is the idea that is behind there is, okay, now we have to try to find the way to make this symmetry breaking in solution, but with much more simple compounds. That this is okay. This is really work in progress for the moment, but it is theoretically it's totally possible. Practically, it's difficult, but possible.
Well, it would be an advantage having it on the surface because you then could separate the systems. If you have them in solution, they will always.
Yes.
So you have problems with having these compartments that you have, as you have shown.
Yeah, but it's better. Actually, it's a problem of surface that it is fixed. So on surface, if you do not allow all this mixing, it means that you will have some R in some place, some S in some place, and you need the diffusion if you want one unique configuration to win on the whole system. So surface is locally good, but globally bad. Solution is locally much more difficult, but it's really necessary if you want one unique bifurcation on the whole system. I think it's the main idea. Yeah.
Okay. Any questions? As I said, there's a discussion period afterwards, but thank you, Raphael. I'm going to use your phone.
Yes, thank you.
Okay. So our next speaker will be Munich Rosen from Copenhagen. We'll talk about geologic consequences of photosynthesis.
Yes. Which ones of these?
I know, I see things for you.
You have a cord like this.
Oh, that one.
You mean yours weren't?
Mine is Danish, and that does, we have a long issue with Sweden, so we don't even share the same electrical appliances.
Not even that.
Not even that, no.
Getting something up here?
It's
Sending, is it me? Are you sending? Yeah, but we need to send.
Like function.
function F7.
Yes, that's good. It's doing something.
Now it went completely.
You can switch another.
Oh, wait a minute.
So welcome everybody to the Nordic joint Nordic.
What did you do?
Nothing.
That's okay. Let's see.
It's getting there.
I have nothing on my own screen, but that's okay. Let's see if I can.
I'll just use once more. Or?
There we go. Yeah, we should probably see where is the thing. Yes. Boom. Boom. What is that?
May I throw out a question?
Down in the bottom.
Let's try this one.
Oh, yeah.
For how
Yeah,
long,
yeah, but
what
that's-
is the history, the historical record, for how long can we trace it back in time?
Ah,
So like million, very short. I mean, I think one has to be optimistic if one can go beyond 1 million years. As it past, with bone records and stuff.
So, inside with CD.
Okay, thank you. Well, I should first of all let me say that I'm sorry that I missed most of this meeting, but of course I'm happy that I get a chance to present my own stuff. So what I'm going to talk about is some of the geologic record we have on Earth, and also on the influence of the presence of life on the evolution of our planet. We usually tended, at least as geologists, to think that the Earth was just a substrate that life was living on, and that life was exploiting this reservoir for various nutrients, but otherwise they had very little to do with one another. But I have this proposition anyway that there was a profound influence of the presence of life on the evolution of the geologic aspects of the planet. So I'll try to run through very briefly some evidence we have for how early life was for sure was present on the planet, and what it did to the place. So we'll just start with this one, since I imagine there will be some physicists here. Physicists usually tend to tell us that they have a telescope or something, and they can look into space and see something that could be several million years ago in one pixel somewhere, and they're very happy about that. But of course, as a geologist, I can take a piece that was formed right here. This is, of course, all time here, and this is more than 1/4 of all time. We have a rock record that covers this whole period of time, and we can take objects and study them, and they will carry a memory of all this part of the evolution or history of our universe. I think that is really the beauty of geology. And the oldest rocks we have on Earth are from here. Earth itself was formed about here, but we have materials that formed there. And what does the place look like? It is in West Greenland. We have a nice mountainous area where we can go and take a look at the rocks. And some of the things we see in this nice mountainous area, one of the prominent things we see would be structures like these in the rocks. These are known as pillow lavas. They form when hot basalt lava pours into cold water, and you have a chill where you form a glass around the liquid, the silicate liquid, and they form these sausage-shaped objects. So this is a indication that 3.8 billion years ago, when these rocks formed, there was liquid water on the planet, that we had already the oceans in place that early in Earth's history. But of course also shows us that there was basalt volcanism. That is not at all surprising, because we know that basalt volcanism has been active on the Moon, on Mars, on Venus, on the asteroids, everywhere where you have planets or planetesimals or anything like that. The first melt to form the logical surface material on a planet would be basalt, and it has been on Earth also this early in the history of the planet. When we talk about, we know, of course, it formed in a scenario like this, where hot basalt liquid is pouring into water, and this could have been a picture taken 3.8 billion years ago, basically. I think also many of the ways we look at our planet, we tend to think of these very strong forces of nature, as we oftentimes call them. When we try to popularize geology, we always have roaring sounds and big volcanoes going off all over the place, all kinds of activity. And I think we have a bias towards thinking that the Earth is a very dynamic planet, and that there's a plenitude of energy for doing all kinds of things, putting it into the cycles and all that. We have energy all over the place. But actually, Earth is a depressingly boring planet. And that's the reason why the rock we saw before has been sitting there for almost 4 billion years, and is still there, and still sitting next to the rock next to it. Nothing has happened to them basically for 4 billion years. So Earth is a planet that's starving for energy. It has very little energy, and I'll go back to that budget. And that's important for understanding the importance of life. So this could also have been a snapshot taken way back in Earth's history. Among the very old rocks, we have some rocks that are different from these basalt. We have actually sediments that have been deposited on the ocean floor in the form of clay, like we have the shales and muds on the ocean floor today. And what you can see inside these clays, I'll try to run through very briefly. Anyway, you can see that they're very well bedded, very well preserved, again testifying to the lack of energy on our planet. In thin section microscopic slides, you can see that these sediments are still preserved in a very, very beautiful lamination. You can see that it contains layers of different color, black and white basically. And we can look at the minerals, and we can see that these black layers have once been clay that laid down on the ocean floor.
Well, this age determination that you mentioned, 3.8 billion years. Is that something that you can get out of these patterns?
You can actually not get out of these patterns. The way you get the age determination for these rocks, which I don't know now, but is that these rocks are very difficult to make determinations on because isotopic systems are not very good in that type of rocks. But they are luckily cut by veins of granite that contains the mineral zircon, that contains uranium, that decays to lead, which stays in the zircon. Then you can go over here to Naturhistorisk Riksmuseet and date the zircons with very great accuracy and precision. So you can get the age. We have cross-cutting granites that clearly must be younger than these rocks that are 3.81 billion years old. So we know that they're more than that. We don't know by how much, but it's probably not very much. So we have this black carbon in the rocks, and of course carbon is an interesting component because on the surface of the planet here carbon is almost always associated with oxygen in the form of CO2 in the atmosphere, or bicarbonate in the ocean, or carbonate minerals in the crust. And usually the only way we get carbon isolated from the oxygen is through biologic action, where you form some carbohydrate or something, and then dehydrate it later as it's sitting in the ground, and you end up with some black carbon, and that was what caused the rock to be black before. So just the fact that we find these old rocks that contain high amounts of carbon indicate that most likely has been life present on the planet already 3.8 billion years ago. And also, if we believe that the carbon is derived from life, from living organisms, it must have been a very proficient life that was here, because if you just had starters in the business of being living, they would not be able to sequester a lot of carbon. But what we see is that these rocks contain up to 8% of carbon. You can actually write with some of these rocks. So they are very rich in carbon. That means that there was a high climate productivity in the ocean at that time. But also we can address the question, is this carbon really biogenic? By looking, of course, at the carbon isotopes. The ratio of carbon-13 to carbon-12 has a very characteristic ratio in all Earth materials. And usually the geochemical processes don't fractionate these isotopes very strongly. And the most efficient fractionation mechanism is biologic activity, metabolic activity. And not only does it fractionate strongly, but it also ends up in a well-defined, recognizable range of values. So when we look at all this ancient carbon in these rocks, it always falls within that same range that biologic activity forms, and that makes us believe that the carbon is from biologic activity. So to get onto what life was doing at that time and what the consequences should be, you should immediately jump onto now. I would suggest accept that life was there, and of course the next question that comes up is, what did life do 3.8 billion years ago? Were we very close to the first life on Earth, or are we at some more advanced stage in the evolution of life? This photograph doesn't seem to have anything to do with life on the surface, because it shows small radioactive particles that are sitting in silicate minerals. You can see radiation, damaged halos around the radioactive particles. So in these rocks that contain high amounts of carbon, we also see that there is high concentration of little tiny micron size particles of radioactive materials. And that is interesting, because one way to look at what life was doing at that time could, of course, be if we could identify some microfossil and say, okay, this was this type of organism. That is impossible in rocks that have been metamorphosed like these have. We only have the carbon, that we have no physical expression of the organisms. Another issue, of course, that basically microorganisms look like microscopic little things, and you can't really tell what they're doing from their shape in most cases. So the only way to address what these organisms are doing is by looking at their metabolic interaction with their environment. So of course that is one of the characteristics of life, as we just heard, that they metabolize things, they take in some A's and put out some B's, or whatever the story goes. And if you can see how this metabolic activity has impacted the environment, we might be able to tell something about the metabolic strategies. And that is why to get back to the story, why these radioactive components are interesting. Because in the surface environment, you have two major radioactive components that might cause damage like this. That's uranium and thorium. And in igneous systems, that means in the basalt or whatever rock we have that form from normal deep geologic processes, uranium and thorium are always key to each other. They always travel together. They are very similar in chemical properties, and they always occur at a fixed ratio of 4:1 thorium to uranium. So you can basically say that they always travel together. When you take an igneous rock like a basalt or granite, something that contains little particles of radioactive materials, these particles will travel as heavy minerals, and they will be deposited in the sediments together. That is if you have a reducing environment. But if you have slight amount of oxygen available in the environment, some of the uranium will be oxidized and form uranyl ions that form soluble complexes that can be dissolved into seawater. And what happens when you have oxidizing environments is that you basically separate the uranium from the thorium. So you leave the thorium close to the source, close to your igneous rock, and you take the uranium into solution in the ocean, and you can transport it out into the ocean basin. And when you have the uranium transported out into the ocean, what happens is that you have a little happy organism living up here, and it dies and not so happy anymore, falls through this zone and starts to decay to become a little zone of reduction power, and it reduces the uranyl and takes it down as uraninite and puts it into the shale down here. And what we see in these shales is that all these radioactive particles, they turn out to be made of uranium, or at least originally we can tell that from lead isotopes. You can tell that the uranium enrichment was primary, and you can tell that as it happens, there was no thorium introduced into these rocks. That means that we had an efficient separation of uranium from thorium. You must have had some oxidation power in some compartment of the ocean. And my suggestion is, of course, that we have a surface veneer in the water where you have photosynthesis going on. That could explain why we can have a high productivity of biologic material. That would explain why we have an oxidizing veneer, and we have a reducing deep water column here where the uranium can go down and be stabilized in these black shales.
So you mean that the atmosphere will still be reduced?
The atmosphere is still reducing. This could not overcome it could not saturate, or it could not basically saturate water and the atmosphere or anything. So the sinks for oxygen were greater than the sources, but the source was able to make local oxidizing compartments. Maybe if I'm correct, no, I'm not correct. Well, anyway, maybe you'll see that later. But oxygen has a very, very low diffusivity in water, and that means that you can build up oxygen concentrations in local parcels of the water without escaping to the atmosphere very easily, or without mixing into the water column as such. You can see that in the ocean today. There's a very, very strong oxygen contrast in the ocean associated with the Baltic zone. And that's simply because it doesn't diffuse very easily out. So that allows it to build up locally in higher concentrations than the global level would be. Oh, anyway, to get back to this story about the importance of photosynthesis for the running of our planet, let's just take a look at the energy budget of our planet altogether. So what we see here, of course, Earth, and a little bit taken out so we can see the interior part. We have always, as geologists, thought that what is running the business here is decay of radioactive components in the mantle and the crystallization of the liquid core to form the solid core in here. And we know pretty accurately, we believe anyway, that the energy contribution for these processes internally in Earth amounts to 87 milliwatts per square meter of Earth's surface. So that is the energy flux that comes from the internal processes. These are these so-called brutal powers of nature, which are really not very brutal because they are very, very low energy flow, as you can see here. Compared to that, of course, we have the solar radiation that hits the surface if you average over the total surface, and on 24 hours a day, you get 340 watts per square meter of insolation on the Earth's surface. So you can see that there's an enormous contrast between these two energy inputs. And Earth geological cycles, geochemical cycles, would have to live on this budget, and climate and everything that happens on the surface environment would live on this budget. So that is, of course, in some ways a pity that you cannot, for the geochemical cycle, you cannot dig into this source of energy. And the reason why you cannot dig into that is basically that the energy, of course, comes in photon packages that have, for the maximum energy of the abundant part of the fraction of the solar spectrum, has a maximum energy of, say, 200 300 kilojoules per mole. And in comparison, most chemical bonds in the surface materials, like the hydrogen-oxygen bond in water, are much stronger than this energy, and that means that solar radiation cannot, in general, with few exceptions, cannot perform chemical work on the surface environment of Earth. It means it basically converts into heat and back radiated as long-wave radiation into space. So it doesn't do anything useful on the planet. So at some point in time, of course, the Earth got a little bit impatient with this situation, having only 87 milliwatts to live on, and have all this sunlight come beaming down, and you couldn't do anything about it. Particularly light, as we just talked about earlier, light needs to channel energy into the metabolic cycle. And if you are an early type of light, before photosynthesis was invented, you would have to find chemical gradients that you could tap energy out of. And these gradients are usually only associated with the place where you have steep thermal gradients, because steep thermal gradients can maintain chemical potential gradients. So that means that light would have to live in very localized places, and places where the flow of energy was changing all the time. It's very uncertain light. That would mean that light would have to be not very abundant when it's based on chemical energy. So light decided to do something about it, and what it did was to make the, not exactly a full chloroplast, of course, to start with, but they decided to invent photosynthesis and develop chlorophyll complexes that can, which effect is to take energy from several consecutive photons and store it up until you have enough energy to do something with it, something focused on with that. And what light decides to do, of course, is to break this hydrogen-oxygen bond and take the hydrogen onto CO2 and dump the oxygen to the environment, and that way it was able to convert solar energy to chemical-free energy, which you see in this column. And if we want to know how much chemical-free energy is associated with this process, we can go down to EKD here in Stockholm and find the thermodynamic data table for this reaction, and it says that it's 1,700 kilojoule per 100 gram of reaction. And that is an obscene amount of energy if you compare to most geological energy conversions. If you have reactions that take place in normal geologic systems, usually you will see that the energies associated with them have something like 56 kilojoules per mole or something ridiculous. But here you have 1,700 kilojoules, so that's an enormous amount of energy that is being sucked out of solar energy. Well, here's the picture I thought I had before. This shows you, of course, the process in action. You can see the base product from this reaction. Oxygen, we have 1 bar of oxygen in all these little bubbles in a small pot of water. So that shows you that there's about half a centimeter of water in this little water pond. And you can see that this oxygen has 1 bar here, it's 0.2 bars, a half centimeter up, and it's not able to diffuse out. It just builds up in the water. And of course, this waste product has to go somewhere and do something. This process is not only energetically very intensive on a local scale, but it's also globally very important. If we look at just a photo of Sweden over here with the strange electrical systems, and Denmark over here, and we have the sea out here, everything is covered with this chlorophyll, which covers the Earth basically green, if you look from above. We have cyanobacteria probably out there in the sea. And the whole Earth is just covered with this chlorophyll converting solar energy to chemical free energy. So if we put that into the budget again, what we see is, of course, we have the 7 milliwatts from the solar, from Earth itself. We have 340, oh sorry, that's a typo. We have 340 watts solar energy. And if you now look at the energy conversion from solar energy to chemical-free energy by living organisms, that amounts to 300 milliwatts per square meter. So that clearly outrivals the energy flow that Earth has on its own. So when photosynthesis was invented and proliferated, started covering the whole globe with chlorophyll, it suddenly changed the energy budget for geologic processes by a factor of probably more than. Most of this comes out as heat, very little comes out in terms of chemical free energy. So probably the energy budget for the Earth's geochemical cycles were multiplied by a very large factor when photosynthesis came into action. And one of these kinds of consequences, everybody who owns a car or a bicycle knows, of course. You take some iron and put it out in the street. The next day, if you are in Copenhagen, if it's a bicycle, it will be stolen, but if it's in some suburbs, what will happen is that it's been rusted up. The oxygen has attacked the bicycle. But of course, before the time of bicycles, oxygen had to go somewhere else, and what oxygen did was attack all the rocks that we have on the surface, and this would be the process known as weathering or alteration. So if we have a planet that starts out with being a basalt planet, like, this is just a little reminder, of course, that we should all know that today we have one extra energy input, that is our burning of fossil fuel, 25 milliwatts per square meter. So we are adding another 1/3 of Earth's normal budget to the thing. So let's not forget about that. Anyway, what happened? We had a surface that was covered with basalt, and that has been kind of perpetually going, basalt being subducted, melting again, come up as new basalt, and so forth. That is the way the plate tectonic cycles work. But as soon as you start performing a large amount of weathering of the basalt, you start making new products that go into this geochemical cycle. And what happens when you have a weathered basalt and start to put it down into earth again and reheat it is that it doesn't melt to form a basalt, but it partially melts to form a granite. And what happens is what I would suggest is that granite we know forms as a consequence of weathering of basalt and remelting. But what I suggest is that granites only started to form in a large way after photosynthesis was informed. That is, that photosynthesis was forcing on the granite production rate. And that is not only based on these energy calculations, of course, it's based on this strange observation that Earth has no continents that we know of before about 3.8 billion years ago. The continents started only to grow about 3.8 billion years ago. So we have an Earth that had more radioactive heat budget, had everything else going from 4.5 billion years to about 3.8 billion years. For those 700 or 800 million years, Earth didn't get its act together to start forming continents, which is very strange if it is just normal physical chemical process. But as soon as life got into the clay in a big way and started channeling solar energy into the chemical energy cycle, Earth could afford to start forming a new kind of product and start to form the granite that covers the continents on Earth today. And I think it's important to remember, before we completely discount this as a stupid idea, to remember that granite is an exceedingly rare rock type. Everybody, if you ask any kid on the street and ask them which is the most normal rock type, they'll say it's a granite. But that's not true. Earth is 6,300 kilometers from the core to the surface. Of those, about 15 or 20 kilometers is granite that covers 1/3 of the surface, and the 2/3 are still covered by basalt. So that's a very, 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 very thin coating of granite that covers 1/3 of the Earth's surface, and the rest of it is still basalt surface. And granite is not known from anywhere else in the solar system or anywhere else we have been looking. not known from the Moon or Mars or Venus or asteroids or anywhere else. Granites are only known from Earth, and they only, as far as we can tell, started built up from 3.8 billion years ago, when life had taken over the control of the atmosphere and the ocean chemistry. So my suggestion is that the reason why our planet looks the way it does today is because life invented photosynthesis, and all these things that we now take for, I was just about to say for granted, but take for our planet, they are associated with this particular invention of photosynthesis. So if we shall look out into other parts of the universe and look for signs of life, I think we have to realize that what we think is characteristic of life on Earth, or of life, is what's characteristic for our type of life, and that is completely biased by this invention of photosynthesis, which was done only once in the living systems. It's not like there's been several distinct groups of organisms that have come up with this idea. Everybody has borrowed it from the original inventor and maybe modified it slightly. But I think it's a serendipitous event that we have photosynthesis on this planet, and therefore if we look at large-scale, say, thermodynamic disequilibria on other planets as a sign of life, that might be true, but the absence of it would not mean the absence of life, because most life, and life before maybe 3.8 billion years ago, would not alter the chemical state of the planet. The chemotrophs just exploit chemical gradients that would decay anyway. They just catalyze them so that they decay a little bit faster, and that doesn't make any significant alteration. So I think again, our planet is the way it is because of photosynthesis. This just tells that the story is true, and we'll stop there before we get
Thank you, Erik. Let's initiate some discussion. Göran?
It's a very fascinating idea, and you are saying that granite is was formed thanks to life.
Mm-hmm. I would say that the production rate of granite is.
Oh yeah, but
recirculation of oxidized.
Yeah.
Then for us who are dealing with the remote sensing, really remote sensing, would it be a biomarker, granite?
I think it depends on. You need to know the intrinsic state of your planet to know. I mean, it could be that you had a planet where the starting materials were such that you would make granite when you partially melt them. Our starting materials are such that you make basalt. In all the rocky planets in our solar system has basalt is a good. The reason why basalt is so common is that it is formed by a partial melting of the most common minerals that you find in meteorites and everywhere else. But if you look at a different solar system, you might have a completely different mix-up of components, and you might not. But I still would say that if I saw a planet that had continents and basaltic areas, I would bet that you would find life there. And I would have to make that bet because you could not negate the
You mean granitic?
Granitic, yeah.
Okay. Mats?
What to me is a bit surprising here that you have a fairly simple rearrangement reaction, CO2 plus H2O, forming CH2 plus O2. Yeah. And in order to get this reaction going, and because of the problem of breaking the bonds, the Earth invents a very complex machinery, this photosynthesis, that we even today cannot do artificially.
Yeah, sure. Yeah.
And this is done in like 3.8 billion years.
Yes. I think that life had a chance to start its activity 4.4 billion years ago. We believe that oceans formed already 4.4 billion years ago. So you have 600 million years to get to the level of photosynthesis. I think if something can happen in 4 billion years, it can also happen in 600 million years. It doesn't. I mean, it's not a significant difference. And of course, you can always say how. I think that's a very relevant but also very difficult question to answer. I think that obviously the main point of this whole machinery, I guess, is to make some ATP that you can use to fuel all these other reactions you need to make all the complex things. But the basic photosynthetic reaction, again, is dependent on a large number of very complex proteins interacting in very complex ways. And how you get to that level is very difficult to say. I think that people believe that the carbon fixation part of it has been established because you need carbon fixation for autochemotrophic life. And some people suggest that the chlorophyll were not originally used for, obviously, they could have served a purpose before photosynthesis were invented, maybe as a thermotactic sensor, because they also absorb in the infrared. And if you are a chemotroph living near a hot vent or something, you need to know where the heat is relative to the cold. And you could have used some kind of chlorophyll to orient yourself relative to that. Some mechanism like that. But how that whole thing was put together, I don't think anybody could even come up with a guess.
So is there a transition, an easy transition from anaerobic photosynthesis to the advanced one by cyanobacteria? Is that something to carry?
It's not easy because you have to combine two systems of photosynthesis. You cannot use, well, water is the electron donor.
Yeah, right.
But it's quite difficult to extract the electrons from the water.
Yeah.
So it could not be done in one blow.
But I mean, if the first photosynthesis was based on sulfur oxidation, sulfide oxidation, so there is not an easy way to go from one substance to the other, or?
No, you cannot go. You just have to. You need to combine both.
You have both photosystems operating separately in organisms that use them for other things. You can use hydrogen as a electron donor for a photosynthetic pathway instead of water, with only one photosystem, and likewise you can do other things with. So, of course, the beauty of the organic photosynthesis is that you merge these two systems, so you are you're not no longer dependent on a source of reducing power. Usually, other systems you need to have an input of a reducing component, which is limiting. But as soon as you can use water, you're unlimited. That's what. But I should say though that I would not stick my head that far out that the photosynthesis we see at 3.8 billion years ago is necessarily oxygenic photosynthesis, but it's some kind of photosynthesis that is able to channel in energy. And I think some suggestions would have that you can have maybe photosynthetic activity based on with other electron donors. You could have them running maybe at up to 10% of the efficiency of oxygenic photosynthesis globally. So it still have a significant impact on the geochemical cycle.
But for the uranium mobilization, you now have also organisms that are able to use uranium as electron acceptors.
Yes. But that would again be probably, I think that if that should be the source of a globally significant amount of uranium in solution in the ocean, it has to be some very efficient rivers to do that. So I think it's not only a matter of oxidizing the uranium and then let it out to the environment, because the environment needs to be able to support them in solution. To the environment, you have to oxidize the environment to transport them on the scale of an ocean.
So who's first now? Axel, perhaps?
At which rate were continents produced, and did that process actually stop at some point?
The rate is very difficult to tell because we have the record of what is left of but we don't know all the processes that were. But if we do from start to now, and we have 4.5 and we have 4, it seems like the curve is doing something like this is a sigmoidal thing, where it comes up quite slowly. We don't know if this continues back to here and it's just been destroyed, but we know that there has not been large volumes of long-lived continents, because in this period of time we have various short-lived radionuclides that are fractionated by the formation of continents. And we can see that these have been homogeneously present in the mantle during this period of time. You can see that they have not been sequestered in isolated parcels. So that shows you that our apparent growth rate of the continent from what we know from the bits that are left now and what we can deduce from that, they match with the chemistry of the mantle in quite great detail also. So I think that it's safe to say that there were not abundant, large, long-lived continents before, and the continents have grown in size and in volume over time.
And the last point on the curve is actually present time, you mean?
This is now.
Yeah.
So does
This
it
is
mean,
one.
does it
Well,
Say
it seems like it's there's a very rapid growth of continents that starts about 2.7 billion years ago and ends about something else, 2 or something like that, where we have the very large production rate of seeds. And interestingly, not that I would say that that is exactly the case, but this is somewhere in the steep part of the curve. This is where we see the oxidation of the atmosphere also. This is the place where life has really taken over control of the ocean atmosphere chemistry. So
could be a good coincidence?
It could be. I think that's what I say. It could well be a coincidence, but it's a convenient coincidence.
Yes, of course.
Well, I have a question about the energy flow. I suppose that the heating from below was higher in these.
Not by much. It could have been maybe 3.8 billion years ago. It could have been 3 times more, or in the beginning maybe 4 times more. But it's not. The heating from below is not. It's not significantly high. It's not orders of magnitude change. And again, most of the energy flow from the inner Earth is dissipated in the form of heat. Very little comes up as chemical free energy. The reason why it comes up as chemical free energy is basically because the mineral assemblies you form at high temperatures are at disequilibrium as a cooler. They divide out and form disequilibrium as a cool. And those are the ones you can short circuit and tap energy from if you are chemotroph.
But what was
like you mean like stabilization reactions?
No, also that if you have olivine and platinum plates that are coexisting at 900 degrees, you take them up to 0 degrees. They're still coexisting, but they're out of chemical equilibrium. Somebody can react them to form some other product, like certain it could be like
in the presence of water.
In the presence of water, if somebody can catalyze the reaction down to the stable product, that's the only way you can get chemical energy if you are chemotroph. It's basically catalyzing these disequilibria that are caused by the cooling of something.
Yeah, the other question. The sun was fainter by, I think, 30%.
I have another talk that I might give tomorrow or something that addresses that question.
But the question is, but would the heat flow below counterbalance in the sense that there would not be an icy planet?
No, not at all. Because if you say the heat flow from below was rather than 87 milliwatts, were maybe 250 milliwatts. And the solar radiation, rather than being 340 watts, could have been 300 watts. So still there's a factor of 3 orders of magnitude between the solar input and the Earth.
So
I think even now we are in Sweden, good old Svante Arrhenius in his paper said that one can completely discount the energy flow from inner part of Earth for the climate consideration.
Yeah, but I was thinking, was the oceans covered by ice?
We don't know. Probably not. Probably not, because at this time of Earth's history, we have only deep water sediment. We know that the water was liquid. Most of the water column was liquid. But we can't tell whether the surface was covered. But we have from slightly younger Earth history, we actually do have shallow water and tidal environments and things to the surface, show that Earth was definitely had open surface water.
Guy?
Yeah, just a remark about, or when we talk about finding, well, astrobiology, finding life also, Mars is the object that we would like to look at. In that time, when you describe complicated life forms on Earth, at that time Mars was also quite different from what it is today.
Yeah.
So would it be, well, I don't know if it's technically possible, but just in principle possible to do these kinds of investigations on Martian material, and would you then expect?
I think so. I think Mars has a big problem, of course, in that, first of all, Mars has a different intrinsic oxygen fugacity than Earth has. Earth is more oxidized than Mars, and Mars is more reduced. And that means that some of the things that we look at on Mars with it's a little bit sidestep, but as an example, people have been very excited about seepage of methane from Mars, for instance. But methane would be the stable carbon gas probably on Mars due to the lower intrinsic oxygen fugacity. So that would not say anything about organisms doing methanogenic activity there. And likewise, I think that the budgets for Mars, the energy budget, of course, for Mars would be even more desperate because due to the smaller volume, the energy from inside would be much, much lower relative to the solar. That would mean that the likelihood that you could live up internally generated energy would probably be relatively slim. But it wouldn't preclude that you can live locally, but it would probably preclude that you can make a globally significant impact on the planet. I think that's it. So I think if you go in and look locally, you would be able to see something, but it would not alter the whole.
No, but I'm thinking of the scenario that you described at that time, when photosynthesis was developed on Earth. Would it be possible that when you look into Martian rocks, to find similar inclusions?
I think so. Absolutely. If you could recover a good rock from Mars and take it back, and we have a number of rocks from Mars, but most of them are excavated from deep in volcanic systems, so therefore they are not very good for that. But if you could do that, that would clearly be a possibility. And on Martian rocks, we also do know we have the carbonate. So we know what the carbon isotopic composition of the water was, and you could probably see that it was fractionated if you found organic or reduced carbon if it was fractionated. Of course, you could also say that Mars being not so far from Earth, if we had advanced life, and we would probably have transferred some of it to Mars during that period of time anyway.
So we see. Excellent.
There's one more source of energy that one should maybe talk about. Before people understood that the sun is actually fed by nuclear energy, they considered the possibility of gravitational energy, which means that the sun is gradually contracting.
Sure. Yeah.
Now the Earth would also be gradually contracting by simply putting heavier stuff more to the bottom and lighter stuff, namely the granites, to the top.
Yes. That is part of the 87 milliwatts actually, because what the putting the heavy stuff in the bottom happened catastrophically very, very early in the history of Earth. The core segregated within the first 30 million years. The core had segregated and probably separated and got into where it is now within less than a million years. So it's a very rapid process, and about 25 to 30% of the 87 milliwatts is the gravitational heat that is stored as latent heat in the core that is coming out now as the core crystallizes. So the core melted by gravitational settling and is now releasing that energy still today.
And maybe one more question about the chemical reaction that actually takes place in the weathering of basalt. Can you actually write this in a simplistic form?
No. Yeah, I can tell you in a very simplistic form. You have iron magnesium silicates and calcium aluminum silicates. That is the basalt. And what happens is that you form hydrous aluminum silicates with either calcium or magnesium or whatever, what have you, based on this during this weathering process, and it's the partial melting of these that leads to the formation of granite. And granite is a very broad term. If you take real like cobblestone granite you have out here, you need also to have a enrichment in potassium, and the original potassium that goes into granite today is caused by the ion exchange properties of these hydrous aluminum silicates, because they exchange sodium potassium with seawater. The water that comes out of a hydrothermal system has a potassium to sodium ratio of 1, and this ocean obviously is sodium chloride, not potassium chloride. That's because the potassium is ion exchanged into the clays. And then you take them down and melt them, and you get the granite up. So that is, if you want to write it out in terms of reactions, we will not. Yeah, but that's the basic principle. And it's actually very interesting from a biological point of view, of course, is that most of our many cellular fluids have a much higher potassium-sodium ratio than does the ocean, and which could maybe be a memory effect from time when things were different. I mean, not only in itself, but actually our blood plasma has a higher potassium-sodium ratio, so the cells like to live in an environment that has a higher potassium-sodium ratio, it seems.
Björn cells use potassium as an osmolyte. No?
Yeah.
So it has also some other different
Yeah,
properties.
it has also, So,
Okay, Axel, we're getting close to 1 o'clock. Is this considered the...
Yeah, maybe then can come some more general questions if people have them, but maybe we should thank Minik again.
Yeah, thank you.
He is around for Minik is around for the rest of the afternoon.
Yeah.
Or at least in
And we'll be at the Frescati campus tomorrow at the Earth Sciences Department.
And
so you're our hostage for tomorrow.
Yes, good.
And so Minik will be speaking tomorrow again at 10 o'clock, right?
Minik's having a lecture at the Astrobiology Research School.
And that's 10 o'clock?
Of course, at 10. I don't remember the exact room, but
Y10, yeah?
Y10, probably right. And in the afternoon at 3 o'clock, you're giving a seminar. And you sent me the title yesterday, which I don't even remember.
The title was Earth Life's Greatest Accomplishment.
Okay. And that's at 3 o'clock.
That's at 3 o'clock.
Yeah.
And what was the title at 10 o'clock? I forgot that, so I have to work on that.
It's probably the same as today.
Yeah.
Okay. So, but that's in the Alman room at the Earth Sciences Department, in their new building, close to the subway station. So if you want to listen, you're welcome to that. General questions, yes. René disappeared. You had one for René. Yeah, but he's gone. If not, I guess, Axel, I'd like to thank you for organizing this meeting and for everyone coming here, and especially, of course, those giving the presentations. And I'd like to applaud all of us. And do you have further instructions for?
There's